Hi again. In this video I'm going to present the result we have got from doing the model analysis that has been explained in the first video. So as you remember, we did two steps of analysis on ultrasonic transducer. The first step is to apply the pre-stress on the structure and more precisely on the piezoelectric material. On the second step we did the model analysis for the whole structure, where we have specified a range of interesting frequencies. Now the job is being completed, and to view the result, right click on the job and select results. Now from the main menu, select steps frame. You can see the two steps we have implemented is being shown in this window. And on the model analysis tab, we can see a number of modes of vibration being extracted, and the value in here represented the resonance frequencies in hertz. To view the mode shape of these resonance frequencies, all you have to do is to activate the animation. So as you can see, for this mode of vibration we got the first torsional modes, because we only have one nodal position along the structure. Nodal position, the place where the response is approaching zero value. And the second mode is a bending mode. To know which bending mode is that, all you have to do is just stop the animation, and you could combine between the deform and undeformed shape by using allow multiple port status. So now you can see the original geometry, and here we expect to get one nodal position, 2, and then 3. So this is the third bending mode. Switch it off, and this is the second torsional mode, and this is the mode of interest, which is the longitudinal mode. We have designed our structure to operate in this mode. Then after we'll have a repeated mode as the second torsional mode, and so on. All you have to do for harmonic analysis is to write down the value of interesting mode, and I'll suggest to also consider the modes before and after the interest mode to see how does these modes can affect your transducer performance. So I'm going to write down these values to use it in the second analysis. Right, the other things we can get from this analysis is the mode shape, and also the precise location of the nodal plane, which is important in case you are planning to hold your transducer. Then the nodal position will be the best choice to not affect on the transducer performance. So to do that, we need to create a path along the transducer, the center of the transducer. Then we are going to plot the response along that path. So I'm going to divide the transducer into two parts, half, so automatically it's going to be selected the zero plane, and then from the tree I can select path and then select points list. Now we need to define the start point and the end point of this path. All we have to do is we can get the coordinates of the starting point, which is going to be on the surface of the outer surface of bolt. Use the query information, select node, and just pick any node on the surface. As you can see, we can get the x, y, and z for this node. The x and y should be in the center and should be zero values, but these values does not match what we expect. The reason is the cutting plane does not pass exactly on the on a node, if you can see. So the node I select while my plane is here to passing 0, 0. This means I don't have a node on the 0, 0 plane. However, you just consider this value as 0 to get your path started from this point and go further to the last point. So from these values, I'm only interested in the z value, as the x and y is going to be considered as 0 values. So just write down this value and then select enter point on the outer surface, front surface. Again, this point does not locate exactly on the plane I'm tracing in, so I'm going to just take the z value and now go back to the path and increase. So my first point will be 0 on x, 0 on y, and I have the value for z. And for the second point, 0x, 0y, and I have you can view your path, which is pass through the center, starting from the pole, the head of the pole, and on the front of the transducer. Now select create XY data and select the path. Within the path, I'm going to select this is the first path. We only have this path. I'm going to select MD4 to get the real length of the transducer, and I'm going to select the include intersection, where the calculation will consider each node or each element, node value that the path pass through. The x value will be true distance around the transducer. The y value, going to select the mode I'm tracing in, which is longitudinal mode, and I'm testing to draw the z, the response in the z direction, the longitudinal response, which is represented by 3. In order to make the drawing more clear, I'm going to remove the background color and adding this dotted line, and also we can scale, increase the font size for the scale, and the line as well. As you can see, we started from the head of the pole, which is where the response is 0.5, and we end up almost like 0.95. I'm going to increase the number of tags, so I'm going to increase it to 1. So this will gives me more precise scaling. I can see the values I'm working on. So the ratio between the output value to the back value can gives you an idea about the performance of your transducer. We're aiming in the transducer to increase the value at the output surface, or what they call it, the working surface, and reduce the amplitude on the back side, because it's not going to be used, so the energy was being delivered on this side is just lost energy. And to do that, you could either change the shape or the material of the back mask. To save your plot, all you have to do is, this is the plot already, just change the name by removing the underscore, and we can write you could also print this figure. So select file, type, and you could save it. could also see more result you're interested in from this analysis by checking the nodal position of other modes and see how close they are from either from the piezoelectric or the electrodes or whatever. Now, to do the second stage of this analysis, the harmonic analysis, all you have to do is to change the step. We have created two mode analysis to be a harmonic analysis, and to do that, right click on the step and then select replace. The harmonic analysis is being considered with the steady state dynamic step. So here we have to specify the range of the frequencies where we are interested in. As I've said before, I'm interested in the longitudinal mode, which is, I've just created this shape to show you how can we get the response, the harmonic response. So this will represent the frequency, and the Y should represent the amplitude. So I'm interested in this mode of vibration, which is the longitudinal mode I've seen before, but I'm going also to extract the modes of vibration, which is the lower mode and the higher mode, to see how close they are from the interesting mode and how can they affect the performance of my transducer. To do so, I've got the resonance frequency for the third bending mode, for the first longitudinal mode, and for the second torsional mode. And I've created a range of points of calculation, 20 points, so that the point of interest or the resonance frequency will be within this range. So starting from almost 10 Hz and goes for 20 Hz, this range will gives me the peak value and the around values of response for this mode. Similar things I did for the longitudinal and for the torsional modes of vibration. I'm also interested to get these curves, but without getting too many points of calculation, as my transducer is large size and this will take long time for doing the analysis. So I'm going to select 10 points of calculation between these modes, and I'm going to distribute these points of calculation in a way they can provide me with more points on the curve and less on the bottom of the curve. So starting from the first point, from the first range, and the upper will be where I'll select 20 points, and the pies is the part where will show me how can I specify either the points of calculation to be equally distributed over this range of frequency, or is going to be distributed highly on the size of the range. And I'll suggest, if you read about the pies and Abaqus documentation, so I did a search within the Abaqus CA user manual about the pies. So you can see there's lots reporting, and the most supporting part is this one. So here it's going to explain exactly, if you select pies parameter to be 1, it's going to distribute the number of points equally over the length of over the range of frequency I've selected. If you increase the value of pies, then the number of points being calculated on the limits of the frequency will be higher than on the middle. I'll use this approach to represent the curve in here. So I'm going to increase the number of points on the limits of the range, or reduce the point on the bottom of the range, on the middle of the range. So I've just also select a 50 Hz space between the end of the first or the upper limit of the first range and the second one, so the point will not be calculated twice. And make it 5, 10. Within the range, I'm going to select 10 points of calculation, and I'm going to select price as 5. So interesting to see a result in this range within this distributed. The second range, which represent the mode of interest, so the range is 20 Hz length, and I've selected 20 points, so each Hertz I've got 1 point of calculation, and the solution will be equal. This is the distance between the range between the longitudinal mode and the second torsional mode represent this area. You can select whatever you want. I just do that to minimize number of points so that the job will take shorter time to be completed. Right. I'm going to change the name as well. So this is the first step to do the harmonic analysis. The second step is to set a boundary condition on the piezoelectric material. So we are going to set the potential difference of the voltage on the surface of this piezoelectric disc. So let's see which disc is this one. So this is the front side of the back disc. I'm going to set 50 volts on this side. You could also use imaginary parts or imaginary values for excitation. In this demonstration, I'm just going to use the real part of voltage. This is the back. I'll keep it the same, 0. This is the front of the first one. I'm going to set exactly 50 as well, and the back of the front disc will get 0. Now the third step is to select the output requested parameters, and as we are testing to see or to extract the electric impedance, we need to get the current through the piezoelectric material or disc, and to get that from the output field electrical, and select the reactive electrical node of charge. I'm also going to extract the electrical potential across the piezoelectric material. Now I'm going to create the job. And I'll check a solution before submitting the job in case of getting any error. Then we could fix it rather than just keep waiting for a long time, and then the running, if there is something wrong, the running will not be completed. You could also monitor progress, see if you got any error or warning message. And because the geometry is really, number of elements in this structures is high, this also will take longer time. So I'm going to pause the video, and then I will continue after I've got the full result. As you can see, before I pause the video, we have got a message saying the electrical potential will not be constrained for contact pair, which is true. It's going to be considered on piezoelectric material, does not be considered on the electrodes. So this warning message need to be read carefully, otherwise your result will be somehow incorrect. So I'm going now to pause the video, and we'll continue after that. Now the checking has been completed, and as you can see, we don't have any error. you only have number of warning messages which are presenting, some of them presenting to the output requested, which is cannot be considered in this analysis. If you wish, you could remove these requested parameters. We'll go back to the output file and then check the stream, which one you select. Okay, then this job is also, I'm going to submit this job through the server, as it's going to be to take long time, and I hope when it's finished I'm going to present the result on the third video. Thank you for watching my video.